All right, so last week we finished up chapter 1, so today we're going to start on chapter 2. Chapter 2 focuses around our first functional group that we're going to introduce this semester. We talked a little bit about it, but now we're going to go into depth here, talking about alkanes. Okay, so kind of the most basic of all of your organic functional groups, because alkanes contain all carbons and hydrogens only, as well as all single bonds. Okay. In terms of functional groups, in terms of reactions, there's not actually very many reactions associated with alkanes. They're kind of boring as far as functional groups go. We will be discussing one in particular. The biggest one, I think that that's used over and over again in practical society would be combustion reactions. So the gasoline that you put in your car would be a mixture of different alkanes. Okay? And that combustion reaction, of course, generates a ton of energy, as well as the carbon dioxide that's all giving us problems right now, right? So besides like blowing it up, there aren't really many reactions with regards to alkanes. So they're kind of a good starting point in that sense. They're simple. But actually the first thing we're going to do anytime we introduce a new functional group is learn how to name it. Okay, so this is going to be your first introduction to the topic of nomenclature. Okay. Nomenclature is one of those things where you have to sort of follow this rules-based process, right? We're going to learn a set of rules, and then we're going to logically apply them over and over again to different situations. You really can't get away with it without knowing those rules. All right? Too many people try to look at the molecule and just kind of guess and hope it's right. And it doesn't work like that. I promise you it will never work out, right? So we're going to learn this set of rules. It's going to seem like a huge pain in the butt at first, but we're going to do it so many times. We're going to introduce every new functional group we introduce. We're going to apply those same rules over and over again, right? So it's just this system that you got to get down. Again, at first it's going to be a little slow and painful. Once you get it down, it'll just be like clockwork every time we introduce a new functional group. Okay? So first thing we got to do is we got to make a little cheat sheet. In organic chemistry, there are all these prefixes. Like I'm sure you guys have heard of like methane or methanol or ethanol, for example, right? Those denote a certain number of carbons in that molecule. So methane, that prefix meth, specifically refers to one carbon. Okay? So we're going to make a cheat sheet of these prefixes and the number of carbons that they refer to. Okay? All right, so again, meth corresponds to one carbon. Eth is 2 carbons. Prop, as in propane and propane accessories, corresponds to 3 carbons. Bute, their butane lighters, for example, is 4. All right, and then from there, it kind of follows like the normal Greek prefix that you would have learned in geometry. I think it's Greek, I don't know really. But that you would have learned in geometry, right? So pent is 5, hex is 6, et cetera, right? So pent, that's 5. Hex, that's 6. 7 tends to be a tricky one, so hept is 7. What do we call an 8-sided polygon? Octagon, so right, so oct is 8. Non is 9. And then dec is 10. And we're going to stop there. Okay? So these are these prefixes. Again, these prefixes denote the number of carbons, all right? Then for each functional group, we're gonna learn a suffix, right? So for example, methanol refers to an alcohol functional group versus methane, which refers to an alkane functional group, right? So the ending, those suffixes at the end, are the thing that denotes a specific functional group. And again, we're gonna start with alkanes. So in terms of our suffix, alkanes, you stick on the ending A-N-E. Okay, so first thing we're going to do is the simplest ones, which are the straight chains, and then we'll kind of complicate things a little bit, all right? But so if we're going to do a straight chain alkane, something like this, all right, again, utilizing our bond line structures that we learned about last week, you're going to have to figure out how many carbons there are in that chain, right? So the tappa-tappin, 1, 2, 3, 4, 5. So that then specifically points you to one of these entries on the chart. So using that prefix pent, and then again, since this is an alkane, you're going to stick that A-N-E ending on there. So this would be pentane. So then everybody take a second and name this one for me. So again, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8. That again points me to one of these entries here. And since it's an alkane, this is octane. Cool? All right, so then take a minute and draw me the structure of propane. We want to be able to go both directions. Structure to name, name to structure. So then we just have 3 carbons, so it will look like a little carrot. All right, 1, 2, 3, because prop refers to 3. Okay? All right, so if it's a straight chain, it's pretty straightforward, right? There's nothing too crazy that goes along with a straight chain. How many carbons are in that straight chain? That points to a particular prefix. Stick the name A or the ending A-N-E on. Right? Cool. So what's going to make it more complicated is when we actually introduce other functional groups or branch points in our molecule. The whole logic behind nomenclature in organic chemistry is that the name of that molecule has to specifically refer to one structure, right? There's no ambiguity about it. If you know the name, you know the exact structure of that molecule. No wiggle room, right? So that means within that name, we have to account for all of those carbons and the position of all of those carbons. All right, so when we get to a branched molecule, it's going to make it a little bit more tricky. And this is, again, the set of rules that we're going to have to learn, and we're going to apply this set of rules over and over again. So, nomenclature rules. And we'll do this example here. Okay. So step one is always going to be, you gotta find what's called the parent chain in the molecule, which is going to be the longest continuous set of carbons that you can count. All right, so step one is we gotta find the parent chain. And again, the parent chain is the longest continuous set of carbons. Right, so by continuous, I mean all in a row, okay? So for example, for this molecule, I could go either 1, 2, 3, 4, that would be one set of continuous carbons, or I could go 1, 2, 3, 4, 5. All right, so then which one's gonna be my parent chain, the blue or the orange? The blue, right? The longest continuous set that you can find in that molecule, that's what's called the parent chain of that molecule, okay? So in this case, since my parent chain has 5 carbons, I guess let me do this. I'm going to do in blue here, my parent, 4, 5. This molecule is going to have the name of that parent chain in there, right? So 5 carbons is again what suffix or what prefix? Pent. So this is going to be a pentane. All right. Now we got to name our substituent, which is the thing coming off the parent chain. All right. So name our substituent. Actually, I'm going to make this in green. Okay, so that would be this last carbon over here. Oh, let's do this. Right, because again, I got to account for all carbons when I name this. So anything sticking off the parent chain we call a substituent, and you're going to go through, you found your parent chain, now you're going to go through and name everything sticking off of it, okay? And for that, we're going to use those same set of prefixes that we learned about before, all right? We can just sort of make a note here. Alkane substituents get the suffix YL. Okay, so this is a 1 carbon substituent, so what prefix am I going to use? Meth. And then I'm going to, since it's a substituent and not the parent chain, I'm going to use that YL ending. So this is a methyl group sticking off of that parent chain. I guess we can just put it here. And then the last thing is we have to indicate the location of that substituent, right? Because so for example, I could also have a molecule like this, which is a 5 carbon parent chain with a methyl group sticking off of it. But these are 2 different molecules, right? So we have to denote the location of that methyl group. So what we're going to do now is we're going to number our parent chain. Okay. We'll get to that more complicated one here in a second. So, if I'm going to number my parent chain, I'm just going to start from one end of the parent chain and start counting to the other end. right? So 1, 2, 3, 4, 5. Right, so then what's the location of that substituent? 3. And so that is how I finish off the name here. This would be 3-methyl-pentane. Right, so we see that the name has like 3 components, and this is going to be the case for most of our organic molecules. It's got the parent chain, okay? It's got the name of the substituents, and then the location of the substituents, right? Those are the main components of the name of an organic molecule. All right, so actually, let's not do this one because it's a little bit too similar. Like that, okay? And I want you guys to get all the way through step 2 for me on this molecule. Find your parent chain and name your parent chain and then name your substituents. All right, so how many carbons do I got in that parent chain? 6, right? 1, 2, 3, 4, 5, 6 carbons in my parent chain. That means anything else is going to be my substituent, right? In this case, the substituent contains 2 carbons. So what would it be called? This is an ethyl group, okay? So now, each example I'm going to do, I'm going to throw a little bit more of a curveball here. In the previous example, it didn't matter whether I would have numbered my parent chain from left to right or right to left. I would have gotten the same 3-methyl out of it, right? In this case, though, it's going to be different depending on which way I number it. So any parent chain, you can number it both ways, and that's a great way to start. So that's what I'm going to do. Put it in the left to right numbering scheme. 1, 2, 3, 4, 5, 6. And then the other direction, 1, 2, 3, 4, 5, 6. Okay? And you can see that depending on which numbering scheme I choose, that ethyl group is either on carbon 3 or on carbon 4, right? So which numbering scheme am I going to choose? We're always going to number our parent chain, and we're going to pick the numbering scheme that gives our substituent the lowest number possible, okay? So pick numbering scheme. All right, so then in this case, what is it going to be, the red or the purple?
Red.
The red, right? Because that gives my ethyl group the lowest possible number. So put the name together. We got 3 ethyl, and then 6 carbons for my parent chain, hexane. Cool? All right, so let's just stop here and do some examples. So first of all, draw me these two. So if I give you the name, give me the form structure. If I give you the structure, give me the name. All right, so these ones these structures I kind of threw you a curveball. So let's see who did that correctly. But first of all, for these ones, 2-methylpropane, my Parent chain is that 3-carbon propane, and then on carbon 1, 2, I have a methyl group. All right, for propyl octane, again, I'm going to start by putting in my parent chain, 2, 4, 5, 6, 7, 8. And then on carbon 1, 2, 3, 4, there should be a propyl group. And how many carbons in a propyl group? 3. Something like that. Okay, so why were these ones curveballs here? So let's take a look. It'd be very tempting to look at this molecule and say 1, 2, 3, 4, 5, 6, 7. My parent chain is a heptane. Okay, but what's the rule for finding the parent chain? The longest continuous set of carbons. So you got to be careful because truthfully, convention is usually to put the parent chain all in one sort of an extended shot, all right? But you can't just bank on that. You got to make sure that you have indeed found the longest continuous set of carbons. And there is a longer set if I start up here, right? 1, 2, 3, 4, 5, 6, 7, 8 for that particular molecule. Okay? So, given that, see if we can't find our parent chain in this second example here. Again, it's tempting to say it's 5 carbons, but let's see if we can find a longer parent chain there. So this one should be 1, 2, 3, 4, 5, 6 carbons. Okay, so actually we'll get to this one here in a second together because it's got 2 of those methyl groups, so how do we deal with that? But based on what we've discussed already, you should be able to get all the way to the end on that one, all right? So take a minute to finish off the name of that particular one, and then I'll show you how we deal with our multiple substituents. These 2 carbons here, so this would be an ethyl group. We're going to number our parent chain. We can go this direction, 1, 2, 3, 4, 5, 6, or the reverse direction, 1, 2, 3, 4, 5, 6. Again, we want to pick the lowest possible number for our substituent. So this would be 3 ethyl hexane. Okay, so over here we're going to make one more sort of step because 4 is to then construct the name. And as we've seen, we've been doing that. The number is what's called the locant. So that goes locant dash substituent and the parent. Notice that the dashes only separate the numbers from the letters, right? It doesn't go between the parent and the substituent. It just breaks it up so that you don't have 3 next to E, right? So again, these little dashes, they're only there to separate numbers and letters. Okay, but then how do we deal with it if we have multiple substituents? So for in this example here, I said I had my 1, 2, 3, 4, 5, 6, 7, 8 carbons in my parent chain. But then I have 2 substituents. This one, which is what kind of a group? Methyl. And this one, which is also a methyl group, right? So I have these 2 methyl groups in there. Okay? So if we have multiple identical substituents, we're going to use di, tri, tetra. We can stop there, okay, to indicate that. So 2 methyl groups, this would be a dimethyl. All right, and we're going to make special note here. We're going to use di, tri, tetra, and we got to include the locant of both substituents. All right, so when I go back here, I got to put in my numbering scheme. 1, 2, 3, 4, 5, 6, 7, 8. Or the other direction. 1, 2, 3, 4, 5, 6, 7, 8. In this case, you can see it doesn't matter. It's 6 and 3, no matter which one I pick. But importantly, I'm going to include the location. So I'm just going to arbitrarily pick one so that it's not too confusing. I'm going to pick the red one, but again, it would be equivalent. Okay, so this is our numbering scheme. When I build my name, I'm going to use the location of both of those methyl groups in the name, right? So this would be 3, 6, dimethyl octane. I got the location of both of those methyl groups, and since they're identical, I use that di to indicate that there are 2 of them. Right, so 3,6 dimethyl octane. All right, so then using that same logic, name this one for me. going to go in and find my parent chain. Nine. I got these two substituents coming off. Each one of them is 2 carbons long, so these are ethyl groups. I'm going to put in my numbering scheme, 1, 2, 3, 4, 5, 6, 7, 8, 9. Go the other direction, 1, 2, 3, 4, 5, 6, 7, 8, 9. In this case, which one am I going to pick, red or purple? Purple, right? Because I want the lowest possible numbers. Get rid of this here. Okay. And then putting it all together, this would be 3, 4 diethyl nonane. Right? The 3, 4, that's my numbering scheme. The diethyl refers to those 2 ethyl substituents. And then finally the nonane is my 9 carbon parent chain. Okay. So then, what would we do about something like this? Okay, take a second and do the first 2 steps for me. Find the parent chain and the substituents. You can actually number as well, so you can do the first 3. All right, how many carbons you got in that parent chain? 5. 1, 2, 3, 4, 5. And then I have 2 substituents. This one here would be called a methyl group. And then the one down here, 2 carbons. So this isn't a methyl group, but an ethyl group. Can do my numbering. So again, the one direction, 3, 4, 5. The other direction, 1, 2, 3, 4, 5. So then which numbering scheme do I want to pick, red or purple? Purple, right? So both of them put the ethyl group on carbon 3. But if I pick the red one, it's going to be a 4 and a 3. If I pick the purple one, it's going to be a 2 and a 3, right? And again, you want the lowest number possible in the name. So that 2 is what's going to break my tie here. Okay, so then how do we put this name together? Same logic as before, right? If we have multiple identical substituents, we would use the di-tri-tetra, but these aren't identical, okay? So if multiple non-identical, we're just going to list in alphabetical order in our name? So, nope, not that one. I have a methyl group and an ethyl group. Which one's going to come first in the name? The ethyl one, because it comes first in alphabetical order, right? So this would be 3-ethyl, 2-methyl, and then my parent chain, pentane. Okay, so importantly, they're not in numerical order based on what the locate was. They're in alphabetical order, your substituents, right? So ethyl comes before methyl because it starts with an E and not an M. All right, so then using that logic, do this one for me. All right, so how many carbons in the parent chain? Awesome, right? So I didn't write it in the sort of like conventional left to right way. We got to be careful. We got to find these 1, 2, 3, 4, 5, 6, 7 carbons as my parent chain. I have this 1 carbon methyl group. I have this 2 carbon ethyl group. All right, and then when I put them together, well, I guess actually we've got a number first. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So it's either a 4 and a 5 or a 3 and a 4. I'm gonna go with the 3 and the 4. All right. So putting it together, again, just alphabetical order. So 4-ethyl, 3-methyl, heptane. Right, 7 is hept. And again, just notice the position of the dashes, right? They're always there to just separate the numbers from the letters. Okay, you don't stick them between 2 prefixes or anything like that, just separating numbers and letters. So then one last curveball here. And so why is this a curveball? Well, first of all, we're going to approach it the exact same way we've been approaching all of these. Find our parent chain. 1, 2, 3, 4, 5, 6, 7. Can name our substituents. This one carbon group would be a methyl group. This 2 carbon group is an ethyl group. All right, the tricky part is when we go to do our numbering. So if I number 1, 2, 3, 4, 5, 6, 7, my red numbering scheme is a 3 and a 5. If I go the other direction, 1, 2, 3, 4, 5, 6, 7, this is also a 3 and a 5. It does. So there's no amount of ambiguity in any naming of organic molecules. So anytime we got a situation, there's some rule that's going to like break that tie. All right. And so in this case, again, we have a tie. We're going to break the tie with alphabetical order. So if and only if you have a tie in your numbering scheme, you're going to break that tie by assigning the lower number to whatever comes first in alphabetical order. All right, so then in this case, the red numbering scheme would win because that puts my ethyl group, which comes first in alphabetical order, on carbon 3. So 3 ethyl, 5 methyl, heptane. All right, so if we go back up to our rules here, we can just pick numbering scheme that gives the substituent the lowest number. Okay, great. But then if we have a tie, break with alphabetical order. All right, so this is sort of our list of rules here. The main thing that we're going to do as we go along is add different endings as we introduce new functional groups, right? So alkanes end in ane. When we get to alcohols, there will be the all ending, right? Besides that, nothing terribly crazy. The other thing is we'll introduce some new substituents that also have sort of different names associated with them. So there are fluoro groups if it's a fluorine, or chloro groups if it's a chlorine. But these set of rules stay the same, right? That's what I was saying. It's going to be a pain in the butt at first, but you're just going to apply that same logic over and over and over again to the point where it'll be drilled into your head by the end of the semester. Okay? Cool, yeah, we can be done there. Oh, we're done, yeah.
Almost like I planned it.